lecturing. Here we go. If we look at this example, our major product is going to be our most substituted position, is where our bromine is going to be. But in this case, that will be a stereocenter, so we are going to get both stereochemistries. And that must be specified in when you're predicting products on a test or a quiz. You can draw it this way. Now remember, if you're showing 4 bonds, and you're showing one thing coming forward, you must show one of the bonds going back, because it's tetrahedral. So you wouldn't have a molecule that has 3 bonds that are in the plane and one coming towards you. I don't want to see that. That's not true. If one's coming towards you, one of these 3 bonds have to be going back, because that's our tetrahedral. Because remember, what we're looking at there is 2 of the bonds being in the plane, one coming towards you, one going back. If you're only showing 3 bonds and we have a hydrogen, it's implied that hydrogen is of course going back. But if you're showing all 4 bonds, because there isn't a hydrogen on this carbon, you have to show one coming forward and one going back. And that's really important. I will remove the point if you don't show that correctly, because then you're not showing the compound the way that it exists. So here you can draw it as drawing both enantiomers. You could also draw it as writing one enantiomer and then drawing plus an enantiomer, as long as it's clear that you do have both stereochemical products that are roughly equal amounts. And again, the minor product would be the anti-Markovnikov, but that would be a very small amount. Remember, we are on the frequency. Oh, we answered this one last time. I didn't mean to start it. Well, I asked this one last time. So what we're looking at with this example, we have 2 positions, and we wouldn't get a carbocation rearrangement, because that would be a tertiary carbocation that wouldn't be more stable. But we're going to talk about rearrangements in the next couple of slides. So our major product is going to be Markovnikov, which would be C. B would be the anti-Markovnikov, and that wouldn't be our major product. Though we would get multiple enantiomers, because if the bromine adds in this position, we actually do form 2 stereocenters, because then the hydrogen adds here. So we would get 4 possible stereoisomers. But that's not going to be our major product, because that's anti-Markovnikov. E, notice that what we added across the pi bond was 2 bromines. There's no way to do that, because we're reacting it with H2. Our first step is our pi bond acting as a base. So we're going to get a carbon-hydrogen bond. So there's no way for us to get 2 bromine bonds. We're going to need a different set of reagents to form this, and we will talk about those reagents, but that's not going to work with HBr, because we will absolutely get a carbon-hydrogen bond. That's our first step. So this is incorrect. Also, notice A. What's wrong with A? So our pi bond. So this is implying that what we had was an SN1 or SN2 reaction at that position where hydrogen was the leaving group and bromine was our nucleophile. That's the only way we can get that product. That's really unlikely for 2 main reasons. One, hydrogen is a horrible leaving group. Hydrogen does not want to leave with a negative charge. It's small, it's electropositive. It's not going to stabilize negative charge. And 2, we discussed that SN1 and SN2 reactions don't occur well at an sp2 carbon, because the sp2 carbon doesn't stabilize a positive charge well, because it's a shorter orbital. Positive charge doesn't want to be closer to the positively charged nucleus, so that's really unstable. And SN2, it's still too sterically hindered with that pi bond. So we don't see a good SN2 reaction there either. So A is not possible. So our only 2 possibilities are C and D. And D isn't necessarily wrong, but it's, D is not a possible answer. That's anti-Markovnikov. But this one would be more clear than this one, because we're not showing stereochemistry at all. So our only possible answer is C, and notice we will form 2 enantiomers, because it is a stereocenter. Now you won't have multiple choice win these, but you do have multiple choice oftentimes in your homework, but you won't have multiple choice on tests or quizzes. So you will have to think about these kinds of things on your own, and thinking about the intermediates are really going to help. You can always think about the mechanism when you're predicting products. What's going to be the first thing? We have HBr, so we're clearly adding a hydrogen and a bromine on the 2 carbons. So that already starts what you're doing. And you have to use up the pi bond because that's where the available electrons are. The pi bond is not retained unless if you do a second reaction to reform a pi bond. And we're talking about one-step reaction. So, like I said, anytime we go through a carbocation, we have to consider rearrangements, which absolutely is going to affect the synthetic utility of this reaction. And if a rearrangement is going to occur, it's going to lead to the major product. So if I ask you to predict a major product, you always have to check and see if a rearrangement is going to happen, because if it's going to happen, that will be your answer, your major product. So if we look at this example, we have a secondary carbocation. Secondary is okay, stable, but we have the possibility of a shift, a hydride shift, to form a tertiary carbocation. And a tertiary carbocation is more stable, so therefore that's going to lead to our major product. So compare it. So anytime you form a carbocation, see if there's any possible shifts that can occur that would lead to more stable. If it leads to a less stable carbocation, it's not going to happen, because that's higher energy. If it leads to an equally stable, there is always a chance you might see some minor product of that carbocation shift occurring, but typically that's not going to lead to your major product. But if a more stable carbocation is going to form, that's going to lead to your major product. And that's true of all the reactions that we ever are going to talk about that goes through a carbocation intermediate. Anytime we have that intermediate, always have to consider that. It could be a hydride shift, it could be a methyl shift. Another common shift, and we see these with rings typically. Let's say we have a very sterically hindered or a very unstable ring, because we have a lot of ring strain, or membered ring. We're next to a positive charge. So what we can have, I like to draw my hydrogens here. What we can have is a shift to form a more stable ring. Put too many carbons. And that relieves the ring strain. Now I left something out. I didn't put my carbocation. Which carbon still has the carbocation? Let's look at 2. 2 has 1 hydrogen, 2 bonds. Now we have a bond between 2 and 4. Right, that's 6. Yeah, 2 and 6. Here's 2, and we took this bond, and this bond was between 3 and 6, but now we have a shift, so now it's between 2 and 6. You see that? Still have a hydrogen. Does 2 have the carbocation? Which carbon has only 3 bonds? 3. 3 is where the carbocation now is. It's still secondary, but even though the carbocation sustains stability, this ring is much more stable than this one. So that's really the only time you'll have a shift anything bigger than a methyl, typically if you're relieving ring strain to form a very stable ring. And then you'd likely have a second shift because this would lead to a tertiary carbocation. But that won't automatically lead because now we're using up that space. So drawing in your hydrogens can really help with some of these mechanisms. Because as you can see, 6 still has 2 hydrogens, so it has a full octet. 2 now has a full octet, but 3 only has 1 hydrogen, still only has 1 hydrogen. Otherwise, typically, all you will see is a hydrogen or methyl shift, because anything bigger than methyl is usually too much energy to move, and that's too high of an activation energy. Again, with the exception of forming a more stable ring. 5 and 6 membered rings are pretty stable. Remember, a shift can only occur on adjacent carbons. So you can have, and it's uncommon, but maybe multiple shifts to get to a final product. But again, that's uncommon with linear structures. But you can't just take a proton from way over here and have a shift. It would have to be adjacent. And I wouldn't have you typically predict multiple shifts. I might give you a product and you have to draw a mechanism that might have multiple shifts. But if I'm having you predict products, I expect you to predict only one shift occurring. But if it leads to a more stable carbocation, it will always lead to a major product. Now this particular position is not a stereocenter, so we don't have to worry about that in our product. And this is the stereocenter because there's two hydrogens. So in this example, we don't have a stereocenter, but if this did form a stereocenter, you would again have both enantiomers because it's still a carbocation. And that step of the chlorine ion attacking is going to be the same. But in this particular case, we have two methyl groups, so it's not a stereocenter. Anytime, any reaction that we ever talk about that goes through a carbocation and intermediate, you always want to consider shift. So when you're predicting products, draw your original carbocation and determine if there's a shift, and if there is, that will lead to your major product. Now, again, synthetically, because you will get your major product as your shift, it's almost impossible to get the product before the shift. So synthetically, this isn't the best reaction if a shift can occur. So if you're a chemist and you're trying to set up a synthesis and choosing the best reagents, you'll typically try to choose a reagent if you're doing this reaction that won't lead to a shift, because you're always going to get a mixture. This will always be your major product, but you'll get a good amount. Remember, major just means you have one in more percentage than the other. And typically major that can be even 5% more is considered major. So that's not really useful. That means one, the highest yield you could get is 60%. And that's not even considering any minor product from anti-Markovnikov. And two, you got to separate these two things out. And it's likely most of our separation methods look at things like boiling point, melting point, and polarity. It's likely the boiling points, melting points, and polarities won't be hugely different, so it will take a while to separate these. It'll probably take you a long time with a lot of columns and doing all kinds of things to try to isolate one of those compounds over the other. So synthetically, this isn't the best route. But if I'm asking you to predict products, always look for that shift. That shift's always going to be major. If we're looking at this example and we're drawing our mechanism, your answer is already there. Again, we didn't form any stereocenters. So if you're drawing the mechanism to show that, well, first off, we have our starting material. And right now, we've only been talking about this one reaction, but we'll be talking about multiple, so this is the way that you should approach it. We have a pi bond that has available electrons and an acid with an available proton. So our first step is going to be our attack onto our proton, because we have that partial positive, partial negative. I don't think that's in there, no. I don't know why this system is doing this. So weird. Electronics can be so useful. And then sometimes they're not. So that's going to form our carbocation. Now remember, if we're drawing the mechanism, we're showing all steps. So all I'm showing is exactly what I have drawn. I am forming a new bond between one of the carbons in my pi bond and my hydrogen. And of course, we're losing HCl. We're going to form our most substituted carbocation, so I'm not even going to show the formation of the least substituted because that's unlikely to occur. So our hydrogen is going to be on carbon 1, allowing our carbocation to be on carbon 2, because those are our 2 carbons of our pi bond. Our first step is always going to be that. Whether we have a rearrangement or not, the first step, the reactive positions are carbons 1 and 2, because that is where our functionality is. We don't have functionality anywhere else. Now we want to consider this is a secondary carbocation. Are we going to get a rearrangement? Well, in this example, you have the product already, so you know you have a rearrangement, because carbon 3 has 3 methyl groups, and here we only have 2. Carbon 2 didn't have a methyl group, and here we do. So we know we have a methyl shift, but if you're predicting products, you should be able to do this without the answer present. So we know we're going to get a methyl shift. It's irrelevant which of those 3 methyl groups you're going to show shift. So it doesn't really matter because they're the same from a chemical standpoint. And that methyl shift makes sense because we're going to lead to a tertiary, more stable carbocation. I'm going to retain the hydrogen throughout this drawing of the mechanism just to be clear in your notes, but you don't necessarily have to draw this hydrogen. I just want you to see where that new hydrogen is. Remember, we have 2 other hydrogens on carbon 1. I'm only showing the one that added. Now our carbocation is on carbon 3. And now it's tertiary, so that makes sense. We also had chlorine as a leaving group, so we have our chloride ion. And now that can attack in our last step to form our final product. And remember, our mechanism should show exactly what our product is, which means a new bond between this carbon and chlorine, and a new bond between this carbon and hydrogen. So we see that. Now again, the hydrogen's not here. We're not necessarily showing it, but it's there. But because we typically don't show carbons and hydrogens, we started with 2 hydrogens in that position, and now we have that one new one. So that's our hydrohalogenations. Now we're going to talk about a very similar addition reaction, but instead of adding an H and a halogen, we're going to add an H and an OH. And that can happen when we react our double bond with water. So this is called a hydration. Now, the hydration does not occur very well with just water. We actually have to catalyze the reaction, and we're going to use acid. So this is an acid-catalyzed reaction. Again, acid-base chemistry is something that we're going to be using throughout this class. We use acid and base catalysts throughout this entire semester. So it's really important you understand areo and you understand our acidity and basicity. And remember, acidity and basicity is based on thermodynamics, meaning at equilibrium, is our products going to be in more amount, more concentration than our reactants? And if it is, then that forward reaction is favored. So it's always really important that we think about this, especially in drawing mechanisms. And I'm going to say something that I'm going to probably say almost every class, and I'm going to continue saying it, and students are going to get it wrong, and I'm going to be mad, and then I'm going to mark it wrong. When you're drawing a mechanism in acidic conditions, you're only ever going to show positive charges, with the exception of your conjugate base of your strong acid, because that's what makes it a strong acid. Because negative charge would not exist in acidic solution. Because an acidic solution means you have a bunch of positive charge floating around. So if any negative charge would be present, it would just react. Think about being in general chemistry lab. What do you not do? You don't take a strong acid and mix it with a strong base really quickly. What happens? I'm sorry. It explodes. It reacts. It reacts really fast. Because a strong acid and a strong base is going to react really fast. So a negative charge in most organic compounds, on an oxygen, on a carbon, on anything other than really our very stable conjugate base, like our conjugate base of H2SO4, it's not going to form. Because it would be very reactive. We would consider that a strong base. We will not have a strong base in an acidic solution. And remember, if we're talking about acid catalyzed, if we say an acidic solution, that means that we have a flask, we have some compounds in small concentration in it, then a bunch of acid, because it's in that solution. So there's a lot of acid present. So we will not show negative charges. On the same way, if we're drawing a basic catalyzed reaction, a reaction in a basic solution, we won't see positive charges because it's unlikely to form. So I don't want to see that, and I'll repeat it almost every class. throughout this whole semester anytime we're working with an acid-catalyzed reaction or a basic-catalyzed reaction. So we're going to talk about why this is acid-catalyzed, and it has to do with stability. But the basic concept of this is that we're going to have a pi bond, and we're going to end up with a hydrogen on one carbon and an OH on the other. And we're doing that with water. But again, because this is going to be acid catalyzed, we won't form OH minus. So we're going to talk about how that mechanism works. So oftentimes you see this with H3O plus, or you see H2O and H2SO4. If you see H3O plus, it's assumed you have a strong acid mixed with H2O. It's unlikely we're going to use an acid like HCl or HBr. Why? Usually we'll use H2SO4, H3PO4. Why wouldn't we use HBr or HCl? Because our HCl or HBr, our conjugate base, our Cl minus or our bromine minus, is also a nucleophile. And we don't want that to attack to get a hydrohalogenation as a byproduct. So if we use something like H2SO4, that is a very stable conjugate base, but it's not nucleophilic. There's too much sterics for it to attack as a nucleophile. So we don't have to worry about byproducts. We want our water to attack, not our Br minus or Cl minus. So typically we won't see these done with HCl and HBr. But oftentimes you'll just see H2O plus instead of seeing an actual acid being given, because there's multiple strong acids we can use that would be efficient here. So typically we're going to proceed via the Markovnikov addition, where our alcohol is going to be on the position that is more substituted. And you can imagine that the mechanism is probably going to involve a carbocation, and it will. And we're going to look at that. So that'll make sense based on that mechanism. Notice this is OH, not OH2, because if we had two hydrogens on that oxygen, it would have a positive charge. And when we isolate this, that won't exist. That proton is going to be deprotonated when we isolate this compound. So we're going to form the neutral compound, not the charged compound. So oftentimes you might see it like H3O plus, you might see H2O and H2SO4 in these brackets. The brackets just means it's a catalytic amount, and a catalyst, the acid will reform in the reaction. So that's what a catalytic amount would mean. Typically, because it's a strong acid and it reforms, you only need to put in a small amount because it's continuously reforming. So even though you're only putting in a small amount, you still have a lot of it there. So you might see it like that, but either way, you're not just going to see the reaction with H2O. It has to have some sort of acid catalysis. As far as chemistry to look at rates, again, these mechanisms were found out that we're going to look at based on experiment. So based on experiment, it was found that Markovnikov addition was typically the major product. The other thing that was found was that the more substituted our pi bond, the faster the reaction, which also leads to the suggestion that we're likely going through a carbocationic intermediate. The last real big piece of evidence that this is going through a carbocationic intermediate as our major mechanism is that we tend to get rearrangements if rearrangements are possible. So remember, anytime we're going to go through a carbocation intermediate, if we have a more stable carbocation that can form, it will, and that'll lead to our major product. So these three experimental details really help chemists understand that this is going through a carbocation intermediate. And that all makes sense, especially based on the conditions, because again, under acidic conditions, it's easier for carbocations to form because they're positive. So we wouldn't form a carbanion that would never exist under these conditions. So the mechanism, again, you can show this as H3O plus, you could actually draw out H2SO4. Either way, the first step is going to be our pi bond acting as a weak base. It can act as a weak base because we have a strong acid present. Because remember, our H3O plus, we're not specifically showing our conjugate base of our strong acid, but it's there. It's going to be pretty stable, so it's just hanging out. So that'll attack, and our leaving group is going to be our water Water is a great leaving group, and that's why we need the acid catalysis. And I'll show the other option in a couple of slides. So once we have that, then we have our carbocation, and if that carbocation is stable, we won't have a rearrangement, but if it is, we have to look out for that. In this case, it's tertiary, so a rearrangement is unlikely. Any rearrangement would be to a less stable carbocation, so that's not going to happen. So we're going to get our nucleophilic attack by our water. Notice, and again, we're forming water in this step, but these reactions are typically done as water as solvent, so we have a lot of water floating around. And at any given point, because our acid is in equilibrium, we have some H2O, we have some H3O+. We don't necessarily have all H3O+. So we have a lot of H2O floating around. Now that's going to attack neutral. We are not, in this reaction, going to form OH-. Why are we not going to form OH-? It's an acidic solution. We will not form a strong base in the acidic solution. Let's say one formed, because really we show with our mechanism what's happening 99% of the time. That doesn't mean there's not a competing mechanism that's occurring, but this is what's leading to our products that we see. So even if somewhere in the reaction mixture an OH- formed, it would react with acid right away. And we would never be able to measure it. If we were measuring the pH would stay acidic. If we were measuring the buildup of charge, it would only stay positive. We'd never see that negative. So I don't want to see an OH-. This is going to attack neutral and not as OH- because OH- won't exist in these conditions. It would just react with an H+ as soon as it would form. So energy-wise, OH- is up here, very unlikely to happen. We're staying with our water, which is down here. So once our water attacks, we do have a positively charged oxygen. I don't know what that little weird thing is that's in my way. Can you leave? There we go. Can we make you go? Oh, that's not what I wanted to do. Sorry. Let's just move it then. Put that there too. So we're going to end up with our positively charged intermediate. That's our oxonium ion, which is just an oxygen with a positive charge, just like our carbocation is a carbon with a positive charge. That's how oxonium ion means. And of course, our last step in our workup, because we won't isolate this. It forms, but this is still higher energy than a neutral compound. This is something that as soon as we would try to separate this compound from our reaction mixture, it's going to lose a proton. So remember, we have water floating around. So that's likely going to deprotonate to reform our H3O+ and our neutral compound. So this is our full mechanism, and this is going to be your final product. So if I ask you to predict products, I don't want this, because this is not isolation. I want this. This is what we're going to isolate. So when I ask you to predict your products, I want you to predict the isolatable products. The intermediate is important. It does go through that intermediate, but that is not the final product. And remember, it's very wrong if you show this answer, and I see this all the time, because you're not showing the formal charge. And if you show the formal charge, you would know that that's unisolatable, and I have to have that proton transfer occur. So it's extra wrong if you show that without the formal charge. You must always show any formal charges on any atom. It always must be shown. So what we have is this compound, and we're not going to go through an OH-. And remember, we can't use a stronger base because of these conditions. But under these conditions, we can form product. Now we do have some problems with this reaction, and one of the main ones is going to be the fact that we have rearrangements possible. But with this acid-catalyzed hydration, it's very useful if we have a very symmetric compound where we don't have rearrangements possible. Then it's useful. If we don't have a very symmetric compound or if rearrangements are possible, oftentimes we're going to look at a different route to add an alcohol to a pi bond that's going to be more efficient. But for now, we're going to talk about another way that we can get the addition to occur over the elimination other than our temperature. We already learned that the elimination is going to be major at higher temperatures, and the addition is major at lower temperatures. And we looked at that in the thermodynamics. But we're also going to look at another way with this particular reaction we can force the forward reaction to occur and therefore increase our yield. Because this whole reaction is going to be in equilibrium. And that's what these arrows mean. Sometimes when we show the forward arrow only, that means that the reverse arrow is so high in energy to go in the reverse that it's not going to occur under the conditions we're using. But under these conditions, these acid catalyzed conditions, the backwards reaction would be very easy. So how can we form the forward reaction? So we're going to talk about that. So we already know we can use temperature. We already looked at that. This is still an addition reaction. If we did the same thermodynamic breakdown that we did with our HBr, we'd see the same concepts, or we did it with HCl. Either way, we see the same concept. Higher temperature will favor the backwards reaction. Lower temperature will favor our addition. But there's another way with water, and we can't really do this as well with HBr and HCl because of concentration concepts. But we can use concentration of our acid to favor the forward reaction of the backwards reaction when we're talking about the hydration. So that's another way we can control the equilibrium. Specifically, Le Chatelier's principle, again, pretty important thing, I don't even think you really talk too much about it in general chemistry, you just mention it. But it's really useful. So we know that if we add more water, that's going to drive the reaction forward. And if we add less water, but more acid, that's going to drive the reaction backwards. Because, of course, this would be plus H3O+. So, if we want to forward if we want our addition to be favored, we're going to use really dilute acid. If we want the elimination, we can use heat and use concentrated acid. And that's going to be the difference. So oftentimes you'll see dilute H3O+. And remember, you're always knowing that with this you're adding H2O. You see dilute H3O+, you don't have H2O present. So that's another way we can not only force the equilibrium, but get the highest yield possible. And in the lab, we really call that, and you can play around with conditions in the lab to optimize them, try to get the highest yield possible. So our backwards reaction, and one reaction that you're going to do in 226 lab when you take it, is do the dehydration of cyclohexanol, which is a backwards reaction, and we're going to heat it. And the other thing we're going to do is we're actually going to have our product, because it's a lower boiling point, evaporate out, and we're getting collected as the reaction's occurring, which drives the reaction to form more product because we're removing it. So we utilize this Le Chatelier's principle all the time in the lab when we can. There's some reactions where this isn't possible to use. Like, it's really hard to have more concentration of H2O and HCl with that hydrohalogenation. But because this is done in the presence of water as mostly our solvent and as our nucleophile, this is really useful. So, just like with our hydrohalogenases, since we're going through a carbocation intermediate, we're going to get both enantiomers if we form an enantiomer. Because again, just like before, we have that trigonal carbocation. So the same concepts that we had in the other examples, we're going to have that to think about as far as stereo selectivity. Again, we might have some, and technically it's not selective or specific because we get the mixture. But as far as our stereochemical outcomes, again, just because anytime we talk about going through a carbocation, we have to think about rearrangements, and hydration is no exception. So if we can form a more stable carbocation, that's also going to happen. So these types of reactions are used. One way it's used is in industry to form ethanol. You can make ethanol, of course, with yeast and fermentation of sugar, and that's done all the time to make the type of alcohol we drink. But in the lab, we don't want alcohol that's mixed with sugar, because of course the alcohol you're drinking is going to have other things in it, typically a lot of water. We actually make alcohol from sugar in the lab. I wouldn't recommend drinking it because we don't let it ferment long enough and we don't distill it enough, and also the lab glassware, you don't want to drink anything out of there. But in the concept, you're going to do it. But if you're using ethanol as a solvent, you want a very, very pure sample of ethanol. So because, of course, you're drinking vodka, which is an alcohol made from potatoes. You try rum, that's an alcohol made from just like cane sugar. So it's both made from sugar, but they have a lot of different tastes. That's because it's not pure ethanol. There's other things in it. In the lab, that's not what you want to use. So industry-wise, what we'll do is take petroleum, crack it, do some stuff until we get to ethylene. And then ethylene, through our acid catalyzed hydration, and typically under pretty low pressure because we are forming a carbocation that's primary. But both carbons would be a primary carbocation. I'm not saying this reaction is fast, but what they do is they'll distill out and separate our final product to make the reaction go forward. Anything that they have left over, they'll then retake, reset it up. So I'm not saying it's a very efficient small-scale reaction, but in industry, this reaction is used to form ethanol, even though we are going through a primary carbocation. There's things that we can do to force that to happen. And there's no possibility for a more stable carbocation. And if we have the addition of the alcohol in this carbon or this carbon, it's irrelevant, they're the same. So this is really useful in industry. Not typically done in small-scale lab, but typically you can just purchase ethanol. It's fairly cheap, so there's really no reason to make this in organic lab. You can buy this from industry. They do a good job of doing it. We don't need to do it. So looking at this example, if we're predicting the major product, again, because we're going through a carbocation, we're going to get more carbon competition. We have H3O plus, it's acid catalyzed. So we're adding a hydrogen on one carbon and an OH here. But remember, with the mechanism, we're going to go through that OH2 plus intermediate. And it's going to be, and I'm not asking for the mechanism in this example. So our OH is going to end up on the most substituted position. And you always want to, when you're looking at one like this, you don't have to draw the full mechanism unless if you want to. You can do that. It's up to you. But you don't necessarily have to draw the full mechanism. Anytime you're going through a carbocation intermediate, however, you should draw at least the intermediate compound. The one that's determining our regioselectivity. So our hydrogen is going to be on the least substituted position, and we're going to form the more substituted carbocation. It's tertiary, and there's really no rearrangement possible to form a more stable carbocation. Other thing, notice, this carbon is not a reactive center. It's not doing anything. Its stereochemistry is not going to change. If that carbon was a reactive center, it might change, but there's no reaction occurring at this carbon. So that stereo center, whatever it is, RNS, is not changing. We're not having any reaction here. So in this case, that stereo center is going to be the same in all of the products. We won't get a rearrangement, so that's where our alcohol is going to be in our final product. And again, the stereochemistry at this position is not changing, but we do form a stereocenter at this position, so we want to show that we're going to get both of those products. And you can do that plus an enantiomer, or you can draw both enantiomers, which is perfectly fine as well. Also notice in this case, we have 4 bonds that we're showing all 4. So if I'm showing this coming forward, I have to show this thing going back. I could technically show one of these going back, but it's really confusing to draw that in a ring. So typically I'll just draw them out. It's much easier to show. And those would be our 2 products. Again, I didn't show the hydrogen, but I know that it's there. There was only 1 hydrogen here. Now there's 2. So I added a hydrogen whether I'm showing it or not. Though that's not a stereocenter, so I don't need to specify stereochemistry. side note, we're showing water attacking. Let's say we had acid, and instead of water as our solvent is ethanol. Well, then our nucleophile is going to be ethanol. And then that would be our final product. Instead of it being alcohol, it could be an OR. Because there's really no difference. So we're showing it with H2O, but if we did it in the solvent of something like ethanol, then that would be our nucleophile. And that's common, and nothing about that mechanism is going to change, except for the fact that where this is an OH, this would be an OR. Now, like I said, rearrangements are possible with our Markovnikov addition of our hydrogen. And for some cases, that's not a problem. For example, a highly symmetric compound, that's not an issue. So if we're doing the addition of the cyclohexene, we're not going to get a rearrangement because any rearrangement would just lead to the same product. And regiochemistry isn't even an issue here because, again, these two carbons. But if we have something that is something like this, we're definitely going to get a rearrangement. But remember, that's going to be just our major. And in that case, it would have two stereoisomers. But where we get the addition at that position of our alcohol. But we'd also get some minor product, and usually in a good amount, of the addition of the alcohol here. That's not very useful. So there's a reagent that we can use to get the Markovnikov alcohol, the alcohol in the Markovnikov position, without having a rearrangement occur. And that's the next reaction we're going to talk about. It's still an addition reaction, and the overall reaction is still adding an H and an OH across the pi bond. But we're going to have a couple more steps to get there. Those steps are going to prevent rearrangements from occurring. And that's going to be based on the specific intermediate that we're going to dissect and look at. It's also going to affect our stereochemical outcomes, however, where we will no longer, if we form a stereochemistry, we won't necessarily get both enantiomers. And that's going to be based on that same intermediate, and we're going to look at that. So this particular reaction is called oxymercuration demercuration. And as it sounds like, this reagent that we're going to react with our pi bond, what do you think it's going to contain? What atom? Mercury, clearly. So we're going to be doing something where mercury is going to be part of this, and somehow mercury is going to prevent a rearrangement from occurring. And we're going to look at that. So in the first step, and it's the first step, the oxymercuration step, that's going to really determine our regiochemistry and the fact that we won't have any rearrangements. We're also going to look at why it's still going to be Markovnikov, and this concept is going to be the same concept we're going to be looking at in a couple of chapters in this. And it's also going to be we'll have similar intermediates in a lot of the other addition reactions we're going to be talking about. So in the oxymercuration step, we're going to add this. And that's going to be the basics of where our alcohol is. So instead of our hydrogen adding first, we're going to add this oxymercuration thing. And then our second thing is going to be our alcohol, and it's going to be Markovnikov. And we won't have any rearrangements, even if they're possible. Then, the second step, which we're not really going to focus on because it's not really going to be important to our regiochemistry and stereochemistry. But our second step is going to be to remove this mercury acetate. And we're going to do that by a reduction reaction. And we're not going to dissect this reaction too much now. But later on in chapter 13, we're really going to look at sodium borohydride, which is going to be our reducing agent, in a lot of detail and talk about how it works even more. But that's going to replace our mercury acetate with a hydrogen. So we're going to really focus on that first reaction, oxymercuration. And you're going to need to know these reagents, because I might ask you to put in the reagents. So here, what we're going to use for the oxymercuration is mercuric acetate. Now, acetate is just this is our acetate functional group. It's our aceto bond O next to an O and one CH3. Acetone has that C-O CH3 and then another CH3. So you see that ACE whenever you see this group. Acetic acid has that group with an OH. So that ACE is that C-O CH3 thing. And you'll see that naming a lot. And we use a lot of that acetone, so that's what that A stands for. So in this case, our acetate is going to be, our mercury is attached to that. So that's what our mercury is going to be attached to, our Hg. But mercury likes to have two bonds, so it's actually going to be attached to two of these. However, in our reagents, one of those acetates is a good leaving group because the negative charge is stabilized by resonance. We're going to form this mercuric cation. And notice it's a cation. So what does that mean? What is our pi bond? Can our pi bond act like? Can act like a base. Can also act like what? A weak nucleophile. A nucleophile is going to be attracted to what? What is our nucleophile attracted to? Positive charge. Mercury has a positive charge. And remember, mercury is a metal, so it's more electropositive. So our pi bond is going to be attracted to it. And this is just what the acetate looks like, but typically you'll see the AC instead of it drawn out. And that's fine, you can draw it like that, or you can draw it out completely. And typically, acetate's the easiest thing to work with. In theory, you could have bigger R groups here, but it's not necessary, and acetate is cheap. So we form this mercuric cation in solution, and it's a metal. Metals can behave a lot different, so we're not really going to focus on forming this mercuric cation as much because it is a metal. But it's a very powerful electrophile, and our pi bond is a weak nucleophile. So a weak nucleophile can react with a very powerful electrophile very easily, because powerful means it's very reactive. So it's going to be attacked by our pi bond. So our pi bond is going to attack our mercury, and notice our mercury does have a lone pair on it. So we're going to form this mercuric ion. But guess what? Mercury is an acid. Not an acid. Is more electropositive than carbon. So this intermediate is not really going to form, and instead the intermediate that's going to form is this. And this is a resonance hybrid. Remember, resonance hybrids are not interconverting between this and this. It's an average. Let's think about our average. Our structure is going to look more like our two structures. If they're not equal in energy, it's going to look more like the more stable structure. That's going to be our average, because we're going to have more of that. So our average is going to look more like that. So what we're comparing is a carbon with a positive charge, that is not a complete octet, or a mercury with a positive charge. Mercury is more electropositive. So it stabilizes that positive charge much better. And it has a more stable amount of electrons around it. So this mercury is much more stable with a positive charge than the carbon with a positive charge. So because of that, we never really form a full carbocation. Instead, we form this. And this intermediate is going to determine the fact that we're not going to have a rearrangement because we don't have a carbocation. It's going to also determine our stereochemistry. We're going to talk a little bit about that. If we form a stereocenter. So this is what our hybrid looks like. And in the hybrid, we have a partial positive charge on the carbon, and of course, it's going to be on the more substituted carbon, so that's why we still get Markovnikov addition. This is unlikely our partial positive charge will be on the least substituted carbon. But we also have a partial positive on the mercury, which means we don't form a full carbocation. Since we don't form a full carbocation, we can't get a rearrangement. If we had a rearrangement, let's say we did. Let's say we had a rearrangement. This mercury mercury can't donate its electrons to the positive charge, it's too far away. So, stability-wise, the carbocation that's being stabilized by resonance with the mercury is going to be much more stable even than a tertiary carbocation. So looking at it both ways in the fact that we don't really form a full carbocation, so we're not going to get a rearrangement. But also looking at the concept that even if we did get a rearrangement, this would be less stable because remember, resonance always stabilizes more. So we don't have any resonance because this is too far away to donate electrons to it. So this is determining most of what we see, and it also is why this reaction is so useful. Because really you have to use, it's so much easier just to throw in water and acid. But it's not going to lead to products you want. Even though it's harder to work with, mercury acetate, and it's probably a little bit more expensive than just water and H2SO4, you're going to get a better reaction because you can't get rearrangements, and that's going to be cleaner. You won't get a mixture of products. So that's the basics of this reaction. But we're still going to get the Markovnikov addition because our partial positive charge is still going to be in the more substituted position. So when our water comes in and attacks, it's going to be here. Now also, water is going to be added second, so we could really react this with any nucleophile. For this reaction, it's going to be water, H2O. We could also react with an alcohol. And you don't need a strong nucleophile for this, so it can be a neutral nucleophile, which is usually what we're using. Instead of hydroxide, we'll usually use just H2O or an alcohol. But really, in theory, any decent nucleophile we could react with. And then that's going to lead to the stereochemistry, and we will not, the regiochemistry, and we will not have that rearrangement. Now, stereochemistry-wise, we have to attack opposite from our mercury because of stereos. So that's one thing to note. So we have to attack opposite from that mercury. And then our second step is just to remove that mercury acetate. And we're not really going to focus on this mechanism right now. The only thing I want to say about it before you go today is that we're using sodium borohydride, and that's added second. And notice this one and this two. There's two main points I want to make before you move today. First off, I don't want to see this without the one and the two, because this reaction won't occur if I mix sodium borohydride with this reagent. Sodium borohydride is going to form, we have a sodium, we have a boron, and it's attached to hydrogen. Sodium is a counterion. Boron is electropositive, more electropositive than carbon and hydrogen. So in this case, instead of having a partial positive on the hydrogen, we actually have a partial negative on the hydrogen, because boron is more electropositive. Because in this case, hydrogen is more electronegative. So that means we have a hydride, an H negative. H negative is very, very reactive nucleophile. So if we mix this and this, instead of our pi bond, which is a weak nucleophile, reacting with our mercury acetate, our strong electrophile, our hydrogen would just react with our strong electrophile, and we just retain that same product. So we must add a 1 and a 2, which signifies we do this reaction, and once this reaction is finished, then we can react with sodium borohydride. And then the second thing is, notice that we have a partial negative on the hydrogen, because boron is more electropositive. And this is important. Hydrogen won't always be the partial positive. It depends on what it's bonded to. Boron's not as electronegative as hydrogen. So practice predicting those products. And we will continue with chapter 9 in the next class. Have a good weekend. Work on your homework.